so like I said, we're going to be taking a look at volumes of solids with known cross sections. All right, so before we get into trying to visualize this, let's just do like a general definition here and kind of what are we going to be doing with this, okay? So in general, the volume of a solid whose cross sections are perpendicular to the x-axis can be found by, so volume is equal to simply integrating from A to B, whatever our interval happens to be, of the area. All right, so it's actually, you're integrating the area of the cross section. Okay, so actually, since I said that, let's actually write that down. This is translating into integrate the area of the cross section. I'm going to do CS for cross section. Okay. Now, what we're going to do is primarily in your homework, maybe one or two challenge questions where you're perpendicular to the y-axis. All right. But for the most part, if you see this question on the AP test, it's going to be perpendicular to the x-axis. All right. Just an overall general thing, because this is just like Calc 1. So we're just trying to get the overall picture here. All right. Now, the deal is these cross sections. Okay. These cross sections are going to be shapes you learned in middle school. Okay, so it could be a square, and we all find the area of a square, side times side. Could be a triangle, and specifically probably going to be an isosceles right triangle. All right, we'll have two legs that are the same. All right, so 1/2 base times height. Okay, or with base and height being the same, it'd be the height squared. All right, it might be a semicircle. Those pretty much are it. Square, semicircle, could be a rectangle, depending on the information that they give you. All right, now let's kind of take an idea or kind of what this is going to be. Okay, let's go with this way first. All right, so this is the visual part that we would be doing. I would be actually doing on the board. So I don't know from here on, like, I don't know how much you're going to draw of this, because like you're just not going to see it. It's going to be a visual thing. Okay. All right, so think of, we're in the classroom. All right, and this I drew on the whiteboard that's hanging on the wall. Okay, so here's our two-dimensional coordinate plane, and here is a function. All right, now what we're going to do is we're going to build cross sections or cut cross sections. All right, out of this, which we've done it in 2 dimensions, right? When we just did the area under the curve, we did rectangles, that sort of thing. All right, but now we're going to do volumes, and we're going to do solids, and we're going to build them off of this piece of paper. Okay, now think of this as being on the chalkboard in the classroom. All right, and I'm building away from the wall. Okay, if I take this whiteboard off of the wall and I lay it down flat on a table, like, which is where I have it laying right now. All right, and if I start building cross sections, all right, let's say I build a semicircle cross section. Okay, so right here, all right, there's a semicircle, right? But I'm going to cut my cross section coming up off of the table. All right, so here the semicircle would be this big, right? But if I cut the cross section here, the semicircle is going to be much smaller. Okay, so when we say our cross sections, all right, now, is this cross section right here perpendicular to the x-axis? It is. So this cross section is perpendicular to the x-axis, but I'm building it up to create a 3D model here. Okay, now if my cross section was a square, okay, so here's a square. All right, so if I drew the cross section right here, this length right here, wouldn't I need this dimension to find the area of the square? Length times width, right? side times side. All right. So the key to this whole entire thing is if I'm doing semicircles, if I want to calculate the area of that, that would be half of a circle, right? And the diameter would be the distance between the curves. Well, for area of a semicircle or for area of a circle, I need pi r squared, but couldn't I calculate half? Because if I know the distance from here to here, then I can clearly get half of that as well. So the key to this is it doesn't matter what the shape is. It doesn't matter what the cross section is. The number I need to help me calculate the area is going to be the distance between the curves. Okay. Now, I want you to see it in a variety of other ways as well. All right. So this is one that if we were in the classroom, we would actually be passing this around. Okay. But like here, let's move that underneath because I don't want those words underneath. Okay. So here, if it was on the board, I would be drawing them. I would be doing my cross sections out this way. I take the chalkboard off and I lay it down on a table. Okay, then here's my cross sections, and I was too lazy to do more than 3. All right, but cross sections and notice the lengths of the size of the squares change based on the curve. All right, and then I got even lazier because I didn't want to draw another 3D model, but it doesn't matter. These cross sections could be a semicircle, they could be the equilateral triangle. All right, so like if we were in the room, you could play with this. We'd pass it around the room, you could see it. Okay, you can visualize it a little bit better. Okay, but there's that. All right, now another way to help you visualize this. Okay, I'm going to share somebody else's nice handiwork here. Whoa, I started spinning too much. Okay, so somebody else was way more energetic when they created these. I stole this off the internet. All right, each one of these is showing an y equals x squared. So just your standard parabola curve. All right. And you can see, look, there's carpet in the background. So they've laid these flat on the floor. Here is the x and y axis. And this one is showing, this first one in purple here is showing squares. So really close to the origin, the squares are smaller. The farther to the right it goes, the squares get bigger. All right. The yellow one is a right triangle cross section, and it might be hard to see that those are right triangles, but again, close to the origin, the right triangles are very small, and as we go, as x approaches infinity, then those right triangles would get bigger, those cross sections. All right, the green one there is semicircles. So again, semicircles are really, really tiny, close to the origin, and the farther to the right I go, the little semicircles get bigger. And then the blue one there is rectangular cross sections. All right, so just kind of a way to try to get you to visualize what this is doing. All right, but again, the bottom line is as long as you know what your cross section is and you know how to calculate the area of that cross section, you're going to be fine, because the distance between the x-axis and that curve is going to give you the number you need to calculate the area. Okay. All right. Anybody have questions up to this point? Just to get a kind of grasp visual what we're doing here. Okay. All right. So this maybe is good. So I'm going to go back to sharing. Okay. All right. So let's go ahead and I'm going to change my window again. My screen, I need it bigger. Let's go ahead and just kind of jump into this and see what we can do with this. Okay. So let's do an example. All right, let's suppose most of these are all going to be phrased in the same way. So I'll be pretty consistent with the way you're going to see these. All right. The region R is the base of a solid. All right. And that part right there is kind of like, oh, hey, this is a clue that we are doing the volume of a known cross section. All right. Because the region that we're dealing with is the base of the solid, because when we had it on the wall and then we moved it down and put it flat on the table, that became the base. Okay, so the base of the solid bounded by the curves. Maybe let's keep them relatively simple. Y equals x squared and y equals an x plus 2. Okay, so nothing too complicated here. All right. For the solid, each cross section perpendicular to the x-axis is an isosceles, I'm going to abbreviate here, right triangle. All right, so for the most part, everyone that we do is going to say perpendicular to the x-axis, although it wouldn't have to. And I have thrown some problems, maybe not today, but later on and then within the next week, there are going to be some homework problems that say they're perpendicular to the y-axis. Okay, same concept, except, you know, you're going to be in different variables. All right, and then they will always tell you what that cross section is going to be. All right, so this one is an isosceles right triangle. Okay, so that's an important piece of information. All right, from there, it's going to say find the volume of the solid. Okay, now I don't expect you to be able to draw those three-dimensional drawings. The main thing we're going to do is we're just still going to draw our flat, you know, two-dimensional XY coordinate plane. So we're going to go ahead and let's sketch that. Okay, let's see here. Parabola, it means on both sides. So I am going to need a little bit over here and then a line. Okay, so. All right, so x squared, that would be what? Parabola upright, vertex at the origin. So I'm going to do a rough sketch like so. All right, label. When you do these on tests and exams or for the AP test and you're sketching something, label that so that they know that that's what you meant for that curve. What? Positive slope goes through 2. All right, so maybe something like that for the other one. So y equals x plus 2. All right, so we have, again, just like we always have had, we've got our points of intersection, which we're going to have to calculate those two. All right, but then this is our region. Okay, now the region R is the base of the solid, right? So this is on the board. I take it off, I lay it flat on the table. This becomes the base, and we're building up. Okay, all right, now representative rectangle. Okay, we're still going to have that, our representative rectangle. All right, now I'm just going to draw our representative rectangle, but basically what? That's going to be the distance between those two curves. All right, now I do have this one already drawn out here, so let's take a look at this. Okay, so here is what I just hand drew. Okay, rough estimate. Here's my representative rectangle. Okay, now if here's our 2 dimension of it, if I take it off the chalkboard and I lay it flat, so here it is flat. Here's the x-axis, here's the y-axis. Okay, you can see the parabola right here. You can see the linear equation going across there. And my cross sections are going to be equilateral right triangles. Okay, so again, what? The distance that we need is the distance between those two curves, or in other words, that representative rectangle. Okay, that's going to be the leg. And how do we do area of triangle? Or yeah, area of triangle. 1/2 base times height. And if this is an isosceles right triangle, which I don't think I said that earlier, then this side and this side have to be equal. So this times 1/2. Okay. All right. So are we good there visualizing? All right. Obviously, we're not going to draw this picture. These are way too complicated to draw by hand. Okay. We're going to draw this, and then we're just going to realize what we are visualizing here and what this distance represents. Okay. It's always going to be the distance that we need. Okay, so there's lots of things I need to do. Let's actually work on these points of intersection right here. Okay, so points of intersection. All right, so if I'm going to, take x squared is equal to x plus 2, move everything over to the left, x squared minus x minus 2. Hopefully this is going to factor. I think it is. Let's see, x and 2 and 1. With a negative on the 2 and a plus on the 1. So that makes it a -1 and a +2. So this is going to be a -1 and this is going to be +2. Okay, so there's our points of intersection. All right, so what am I going to do? I'm going to calculate the volume. And I'm going to come over here because I want a little bit more room in here in case I need to write something. I'm calculating the volume. I calculate the volume by running the integral from whatever interval I'm on. So from -1 to 2. All right, now I need to integrate the area of the cross section. So I'm just going to write it like that for right now. The area of the cross section. My cross section is the isosceles right triangle. All right, now let's come over here and stop and think about this for a minute. I'm just going to kind of write this down. I could have done it in a different color. Area of our isosceles right triangle. Okay, so let's just visualize this. Area of a regular triangle is 1/2 base times height, right? But because it's isosceles, this B and this H is going to be the same number. So if I refer to it as a height, because it's the height between, distance between there, couldn't I do H squared? So couldn't I say my area is 1/2 H squared? It's going to be the same thing, right? Because my B equals my H. All right, so now if I think about the area, all right, I can now replace this area formula with whatever I've done to calculate this here. Okay, so a -1 to 2 with a 1/2 H squared dx. All right, which probably at this point does not need to be a dx because I just changed my variable to an h, so probably ought to be dh. And my whiteout is no longer working. There we go. All right, probably I'd change that to a dh just so that the variables match there. Okay, now how do I find this distance? Okay, we find that distance the same way we have been all along. We do what? We do top curve minus bottom curve. All right, because top curve would give me this whole distance. All right, if I did this bottom part, it would give me that. If I subtract the two, it's going to give me what's left over. So top minus bottom. All right, so, and I can pull out the 1/2. So let's go ahead and pull out the 1/2. All right, so I'm going to have a 1/2 on the outside, -1 to 2. All right, so I'm actually literally going to write top minus bottom just so that we're on this first one, so that we're following everything we're doing. All right, now I'm squaring it because the height there needs to be squared because of what we did over here. So top minus bottom squared. All right, I'm going to go ahead and put this back in terms of x because when I find top minus bottom, it's going to be in terms of x. Okay, so my 1/2 is still here. -1 to 2. All right, my top curve was the x plus 2 minus the bottom curve, which is the x squared. That whole thing's got to be squared. Okay, and then of course we're not going to do the calculus on integrating that because you can integrate that, you can plug that in. That's not the problem that we're trying to learn here. If you wanted to work it out, I think you should get an 81/20, or as a decimal, it's going to be about 4.05. Okay, so if you are going to try that later at some point in time, you can. Okay, but basically, this is a think through thing. Okay, you've got to really just stop and think about, okay, what is my shape? How do I find the area of that shape? Okay, so put that in there. And then what distance in that area formula do I need? All right, whatever distance that is, whatever distance you're going to need, it's always going to be, you're going to be able to find it by subtracting the two curves or running the curve, doing the function itself, depending on what the picture looks like. Okay. All right. So are we good so far? Do we have any questions? Okay. Silence, I guess, is a good thing. All right. So let's try this again with a different shape. Okay. Because that was an isosceles right triangle. All right. The shapes are going to change on these. All right. So let's take a look at, say, a paperweight. Is made so that its base is the shape of the region between the x-axis and y equals 2 sine x. Each cross section perpendicular perpendicular to the x-axis is a semicircle. Okay, so again, they're pretty consistent with this perpendicular to the x-axis. All the examples I do are going to be that way. The vast majority of the questions you have to do are going to be that way. They're going to give you what the cross section is, It's a semicircle, okay? And it didn't, this time it didn't say the base of a solid, but it says the paperweight is made so that the base is the shape of the region, okay? So you've still got that kind of same phrase in there, all right? Find the volume of the paperweight. Okay, so needless to say, yeah, lots of writing, big paragraphs here. Okay, you're just going to have to kind of get used to that, but go through your story problem, pick out all the important pieces of information that you're going to need. All right. Obviously, we would need to know the regions between the x-axis and that y equals 2 sine x. Okay, so first of all right, we need to be able to sketch, roughly sketch sine x. All right, 2 sine that 2, all right, really isn't going to have any bearing on it. It's going to do the stretching thing, make it taller, that sort of thing. So just in general, if I try to draw this thing in a 2-dimensional sequence, all right, well, so what? What's the period for sine? Do we remember? Do we remember the period for sine? I know you went through trig during the pandemic last spring. All right. Dead silence. I'm taking it that means nobody's remembering. The period, where does the sine wave start over at? It starts over at 2 pi. All right. So in other words here, let's draw it really, really small here. Okay. So here would be pi. Here would be 2 pi. All right. So the sound, sound. I keep saying sound. Sine does this. And then what does it do? It keeps going and it keeps going and it keeps going. And then it repeats over here, right? Okay, so I'm going to need between the x-axis and this. So basically, I've got this shape going right here, okay, for our paperweight. This is going to be our region that we're going to lay flat. All right, we're going to have a representative rectangle. I didn't label that. Let's label it. Y equals 2 sine x. All right, let's put our representative rectangle on there. So basically, this was just going to be the distance right here, right? So I don't have to do top minus bottom. It's just going to be the distance for the curve f of x. All right, now this one, I know I said we weren't going to draw these visually, or I'm not going to make you do this, but with this being a semicircle, I do want to do this just a little bit. Let's say this is on the board, and let's say I'm going to try to lay it flat. All right, under normal circumstances, I'm not going to have you do this, but since we're still explaining, okay, so there's my y-axis, there's my x-axis. All right, there would be the first half of the sine curve right there. All right, now, what were my cross sections? My cross sections are semicircles, right? So I think I want to do this one because we've got a semicircle, or what appears to be a semicircle is really not. All right, and then you've got this. This is my cross section going up, right? Now, what is that? The cross section is a semicircle, so it's half of a circle. All right, so let's just talk about the area of a circle, okay? So area of circle. Okay, what is that? That's pi r squared, right? Okay. I only want half of this because this cross section is a semicircle, so I only want half. Okay, so I'm going to do 1/2 pi r squared. Okay, now the distance that I'm going to know is going to be this one right here, which is the diameter of my cross section. Okay, I said that this distance is always going to give you the number you need, but there again, in this one, you're going to have to do something to that number, right? Because this is the diameter. So to get this right here, what? It's f of x, if that was called f of x, or it's going to be 2 sine x, however you want to look at it, but I got to take half of it. Okay, so I still have my 1/2. I've still got pi. Now I need the half of this distance. Well, the entire distance is 2 sine x, but I want half of that. So that's my radius, and I'm going to square it. Okay, does everybody follow me? So this is my overall area of my cross section. That's going to be my a of x function. That's going to be the area of the cross section. But I analyzed, first of all, what the heck was going on here. Okay, this distance is the diameter. So I need half of it to get the radius, square it, pi. This 1/2 is because it's a semicircle and I only want half of that area. Okay, So now I'm going to go to a new piece of paper, except we kind of need to keep that. So I'm going to kind of keep that. Let's keep that right there. Ooh, did too much there. All right. So what are we going to have here? I'm going to be, oh, we know our points of intersection, right? Points of intersection are going to be 0 and pi. Okay. All right. So let's move that highlighter out of there. Okay. So my volume calculation here, I'm going to integrate from 0 to pi. All right. I'm going to go ahead and write a of x. All right. Dx. All right. Now, this is going to be the area. So then I'm going to have the integral 0 to pi, 1/2 pi 2 sine x all over 2, and then square it, and then dx. Okay, that way I didn't have to go to a dr or anything like that. I didn't use the r. I just kind of did this over here first. Everything's in terms of x. All right, now 1/2 is a constant, so we can pull that out. Pi is a constant, so we can pull that out. All right, so if I pull those two things out, 1/2 pi, I'm integrating from 0 to pi. All right, then I've got a 2 sine x all over 2 quantity squared dx. Okay, now you could just go ahead and integrate that too. You could also go ahead and simplify that just a little bit, right? Because if I wanted to simplify it, couldn't I take this 2 and this 2 and cross them out? So, I mean, if I wanted to go ahead and mess around with some more algebra and simplify that down a little bit, that I could, or I could just integrate right there as well. Okay, so if you're doing it by hand, maybe simplify it more. If you are using your calculator, then it really wouldn't matter at that point. So sine x quantity squared dx. Again, we're not going to do the integration because that integration part should be fine. I don't have the fractional value of that, but if I did it right, it should be 2.467 roughly. Okay. All right, so is everybody following me so far? We're awful quiet this morning. Just checking. All right, if you're not, you got to unmute and let me know so that I will stop and do something over. All right, now let's do another one because we've done, what have we done? We've done an isosceles right triangle. We've done a semicircle. All right, let's go ahead and try one that is a square. All right, so we'll just do one of the 3 most common. Honestly, those are your 3 most common cross sections. Okay, so we'll do another one here. Let's suppose that it says find the volume of the solid whose base is bounded by y equals x plus 1 and y equals x squared minus 1, and whose cross sections, we're going to start abbreviating here, perpendicular to the x-axis are squares. Okay, so depending on how they phrase it, how they word it, they can sometimes get it down to just like a couple sentences here. All right, so our cross sections are squares. So that's the part that you're looking for. All right, find the volume. We're finding the volume of a solid whose base. Okay, so there's that keyword that tells you, oh, hey, I've got to integrate the area of the cross section. All right, again, we are perpendicular to the x-axis. So for the most part, you know, like I said, that's going to remain the same. And then, of course, we've got the 2 curves. Okay, so on this one, I'm just going to draw the 2-dimensional shape here. So let's see, what do we got here? We've got, again, a parabola. It's going to be on both sides, first and second quadrant. So we'll kind of put this in the middle. Okay, so shifted down 1, upright parabola. Okay, so there's the y equals x squared minus 1. All right, again, slope-intercept form there, +1 slope goes through 1. Okay, so probably really bad here. Yeah, really bad. I mean, they're rough sketches, but yeah, at the same time, I kind of want to make them look, you know, respectable here. Okay. All right, so bounded by these 2. So this is the area. This is the base of our solid. All right, representative rectangle. all right, is going to be these two curves in between these two curves. So we are going to do a top minus a bottom. We're going to do a top minus a bottom right there. We've got some intersection points. We're going to have to find the intersection points. Okay, so we'll have an intersection point there. We'll have an intersection point there that we've got to figure out. Okay, and this is going to be, we're building up a square. Okay, so we'll get into that in just a little bit. Let's go ahead and find those points of intersection. All right, so points of intersection. Well, we're going to have an x squared minus 1 is equal to an x plus a 1. All right, so moving everything over to the left, I'll have an x squared minus an x. Subtract 1 from both sides, I'll have a minus 2. Looks like this is always going to factor in. The intersection points are not always going to be negative 1 and 2. All right, even though it looks like in these two examples it is. Yep, so negative 1 and 2, again, strictly coincidental. Okay, so right here is going to be negative 1. Right here is going to be a negative, or not negative 2, it's going to be a positive 2. Okay, so coincidental there. All right, so again, I'm going to come over here a little bit so I've got more room, my volume. I'm going to do what? I'm going to integrate the area of the cross section. All right, my intersection points are negative 1 and 2. All right, I'm going to integrate the area of the cross section. Okay, so now let's come over here and focus on that area of my cross section. So the area of a square. All right, lots of different ways to do this, but what? Generally what? It's the side squared. I mean, you could do length times width, but since it's a square and it's going to be the same, the area is going to be the side squared, right? And this side right here, okay, that'll be one side. The distance between there is going to be top minus bottom. Okay, so I could be doing, let's just go ahead and do it right here. Let's do, so the x plus 1 top minus the bottom curve, which is x squared minus 1. Ooh, I want parentheses around that. Okay, so top curve minus bottom curve. All right, and then that whole entire thing is being squared. All right, so you could focus on it out here, not in the integration here. Do your math, think about what's going on here. All right, and then replace over here. That might be a good idea. Initially, I think I do want to actually see this. So I want to see you so that I know that you are doing top minus bottom. All right, so go ahead and include that line over here, and then you can simplify in your next line. Okay, so I'd be integrating from negative 1 to 2. That x plus 1 is showing me that you're doing the top curve minus the bottom curve. All right, and then you are squaring it because we needed side squared, and this is going to be a dx. Okay, of course, simplifying this, that'd be a negative x squared, that'd be a plus 1. So if I clean that inside up a little bit, and you might want to clean it up if you are putting it in your calculator, all right, just a little bit. I don't know, negative x squared plus an x, and then a plus a 2. And then again, quantity squared dx. Okay, either one. You could have put this directly in your calculator. You could put this in your calculator. All right, and again, we're not doing that integration because you can all handle that. All right, you're going to get a roughly 8.1, and I don't know why I only went out 1 decimal on that, but I did. All right, remember AP test, we go out three decimal places, but for whatever reason, I rounded it to 8.1. Okay, so really a good idea on these, if you figure out that area of that cross section, not in the calculus. All right, and that's why they invented the margin of your paper. Okay, do the area, figuring out the area in your head. All right, figure out what it's going to be and then place it inside the calculus there. I think it's going to be a whole lot easier. All right, I'm going to stop sharing.